Okay, so let's talk a little bit about mixing. I think this is the last thing that we're going to get through here before we have to quit. But so mixing is the other process. Mixing in water systems is simple. So unlike, if we're talking about volumetric mixing of two different bodies of water, and we're thinking about the solute compositions or isotope ratios of dissolved constituents or something, where we get concentration dependence in our mixing, and they have nonlinear systems. I think there'll probably be some examples that kind of come up. For water isotopes, we're dealing with water. The concentration of water in water is always about 1. And so when we mix two bodies of water, their isotope ratios combine in a linear fashion, and we just get a simple linear mixing relationship. Okay. And we can apply this in many, many different cases. Ultimately, usually what we want to know is what is the source of the water, what mixtures of sources. Here's an example when we're looking at groundwater here in nasty Gary, Indiana. But we can see a mixture between deep water that's actually isotopically quite light. And this is recharged probably during the kind of last glacial period. And surface water, which has isotope compositions that look like the Great Lakes. And then we see mixing in between where people are extracting water and recharging it artificially into wells and stuff, and we're getting mixtures. Okay. So we can tease out contributions from different sources in this way. We can do a similar thing in the atmosphere. And so here's one example of a good number of studies now that look at how atmospheric transport affects rainwater isotope composition at different places. And if you think about what we've described so far and talked about so far, the history of the air mass is what really is going to set the isotope composition, right, of the water that falls from it at a certain place. Here in Salt Lake City, it's going to depend on whether that air mass came a long way from over Canada and then came down to us, or whether it came right up from the Gulf of California. Right? That transport path and the history of rainout for the air mass is what's going to set the isotope composition. And so here you can see for Ithaca, New York, kind of different clusters of different types of storms have been classified meteorologically here. And you can see their paths. And you can see the isotope compositions of the rain that falls in Ithaca delivered by those different storms. Okay? And you can see that we can classify these in kind of an n-member way into different storms. But there's variation and gradation. And some of those lake effect storms, look a little bit like warm sector storms and may have some similar properties. And there may be mixing for different sources. And so when we see a lot of variability along a meteoric water line like this is often reflective of mixing from different sources of water. Okay. Here's another example around here. So let's think about rain and our Raleigh model and how this works in the real world. I think this is going to be the last point here. So again, we have this temperature effect, this temperature relationship, where changes in temperature drive rain out and give us isotope values that are correlated in rainfall with the temperature at the sites where the rainfall is happening. And so we can take this and we can put it into a simple GIS model, or you can do this in a spreadsheet if you wanted to. So let's say we have a transect here. I've got an idealized transect drawn on this map for a winter circulation system, right, in North America, where we've got air coming off the Pacific coast there, and it's following a sinuous jet stream and coming up into Canada. It's diving down into the Midwestern U.S., bringing cold, miserable air to Indiana, where I used to live, and then exiting off into the New England seaboard there. So according to our Raleigh model, right, the only thing that's changing isotope compositions in the atmosphere, right, and in rain is changes in temperature. As it cools, the air saturates, we lose water, we distill heavy isotopes out, and the air mass evolves over time. Okay? So we can do this in a model. We can do a theoretical description of this. The color field in the background of this map is temperatures, January temperatures or something, from across this area. And so I can pull the temperature value at each place on this trajectory. I can take the initial temperature of that air parcel when it left the Pacific Ocean, right? And I can assume it was saturated at that point. And then I can use the saturation vapor pressure equation and calculate how much loss we have as that air cools. Okay? And so this is what we get. This is the relationship that we get. So the black curve there is our temperature. Actually, this is, I guess, the fraction, or no, that's the temperature, right? Plotted on the left axis. F is the predicted fraction of the water vapor remaining based on our saturation vapor pressure relationship. And so what you see is as we move off the ocean, okay, we start to lose water as the air mass cools, forces rain, and we lose water, and the blue curve there is the fraction remaining, and so every time it cools, we lose a little more water, and F drops. And then we take our Rayleigh model and we just turn that into isotope numbers, and the isotope numbers are the red curve, delta 18O, okay? Delta 18O is dropping as F drops, right? This is our Rayleigh expression here. Okay. So how does that actually compare with data? Let's take some data. So here's some things to kind of help you see. There's the trajectory. Now we've taken the data. So this is, again, an interpolated estimate of winter delta 18O across this transect. And that's now the red line. Right? And this is from our IsoScape map where we've actually taken real data and plotted up what January rainfall looks like, or snowfall in many places here. Okay, so what do we see? Here's our Rayleigh model. It's now in blue. I changed colors on you. Okay. Does the Rayleigh model work? What's that? Yes. Yes and no. Okay. Very good. So the Rayleigh model works beautifully here, right? For the first 1,000 kilometers or so, what we see is a really wonderful match. Okay. And then from there on, things fall apart. So let's think about that. Why? Right? Well, what are the assumptions in our Rayleigh model? Like, what is the, what's the description here? What are the assumptions inherent? Okay, so we've got equilibrium fractionation. Okay. Yeah? Yes? Either of the gentlemen in the back or Rose? Only one source, right? Okay. So that's going to be the key one here, is that our Rayleigh model assumes that we have an initial R, R0, right? We take that water vapor, right? We stick it into a parcel of air, and we're just watching how it moves or how it evolves over time, right? There's no additions, right? There's no mixing, right? So it turns out that the atmosphere along the Pacific seaboard here behaves pretty much like our Rayleigh model would dictate, at least at this time of year in this particular circumstance, right? We have a source of water vapor from the ocean, right? Charges up those air masses, and as we lift them up over the, like I said, it's not the Cascades up there, the Rocky Mountains in Canada, we start to cool that air, we start to produce rain, and really what we're seeing is just a progressive loss of water, right? But once we get up over the Rocky Mountains, at this dividing point here, we start to see things change. Okay? So that's telling us that we have some kind of a boundary in the system, some kind of a change in the processes. We're no longer really meeting the assumptions of our simple Rayleigh model. And we see, in fact, that the isotope compositions, the precipitation, when we get down to this part, right, are starting to go up. We're getting higher values, right? So what's a way that we could get higher values in the eastern part of this transect? What do we have to do? What's that? Another source, yeah, exactly. So we have another source. We have another source that's experienced less rain out, okay, and is bringing in water with a higher delta 18O. And so, in this case, although I've drawn this idealized transect, and sometimes the circulation looks like this in this part of the world, even if you have a circulation pattern like this, it turns out by the time you're down here, if you're producing moisture, most of that moisture is producing rain, most of that moisture is coming from the Atlantic or the Gulf of Mexico. Okay? So you're combining cold, dry air that's coming down this way, and you're adding moisture back to it, and that's how you get rain. Right? In fact, you can see that our Rayleigh model itself, right, doesn't even predict any rain after you get over the Rocky Mountains, because we've cooled to the coolest temperatures that air is going to experience, right? And again, thinking about our Rayleigh model, you can't really do anything with it after that. So we're adding moisture back from a source or multiple sources. And so the Rayleigh model works well in the absence of mixing, but we need some other sources in order to explain the real trajectories. And so we can think about what those are. There's multiple possibilities. One really important one is evapotranspiration, or recycling of moisture from trees, soils, open water bodies back to the atmosphere. It turns out if you look at the reanalysis data and do the budgets, about 70% of the water in the atmosphere has been cycled through terrestrial ecosystems, right? So it's fallen out as precip and been evapotranspired back into the atmosphere. We can have other kinds of mixing, eddy diffusion. So the atmospheric transport is not a laminar flow system. We have turbulence, and that turbulence mixes things through diffusive eddy diffusion process. We can think about other kind of systems where we have mixing contributing, and again, this is where we start to get into this kind of combination of processes interpreting our data. Groundwater, river water. We can think about, if we're thinking about stream systems, I think a really interesting one in places like this is the potential for urban runoff and effluent to contribute to systems, okay? So we can often, if we take a kind of idealized model, like we've seen here for the Raleigh model, right? And we try to apply it to our real data, it seldom works perfectly, right? But often what we can see is discrepancies and offsets that point us toward other processes that might be important. These are some here. Okay. This is a classic example kind of showing the importance of evapotranspiration in the Great Basin. It's a transect precipitation and groundwater isotope ratios from the California coast through Nevada and Utah. What you see is you get a very, very flat isotopic gradient once you get up and over the Sierras, right? And that's reflecting the fact that we're in a closed basin system here where things are basically balancing out, right? The amount of rain out from the air masses is balanced by evapotranspiration flux back. And that gives us very little isotope effect. And then just one last example. Here we're looking at the North Atlantic and a map of precipitation isotope ratios, again, across the North Atlantic, estimates, model estimates. But if we draw a line across the North Atlantic, what we see is the hydrogen isotope ratios and precipitation go from kind of lower values off the New England seaboard, or I guess that's Canada here, up to pretty high values by the time we get out to the middle of the North Atlantic. So what's happening in between? What's the feature that's giving us that rise? So that's where the Gulf Stream is kicking up to the north, right? We've got warm ocean water up there, and we've got high evaporation rates off of the North Atlantic that are recharging this air mass with new vapor, right? So we've got another source of mixing. Okay, and so this break is going to be our coffee break. Again, I have